15.4 application of double integral. Number one, mass of a thin plate. On exam. So, well, for a thin plate on the XY plane, this is the thin plate right here. Well, we can get the mass of this thin plate, right? We can have a sample mass right here. Sample mass it's just a density times area. Well, we know the density is given by a function that every mass has a density, and then this density is going to be a function in terms of x and y. So the density here is the rho xy. The area is dA. Let rho xy be the density of the plate. At each point x, y occupying a region D on R2, then is mass is m is equal to, well, we got to sum up all the sample mass there. Double integral over the region D, rho xy dA. Now, example. Find the mass of a thin plate with density rho xy equal 3xy occupying a region bounded by x equals 0, y equal x, and y equal 2 minus x squared. Sketch D x equals 0. That is the y-axis. Y equal x. Oh my God. Okay, so y equal x. And then y equal 2 minus x squared. From the description, right, it got to be a region bounded by the three curves. So the region is going to be this one. This is the region, right? region D, and that is the thin plate. dA is dy dx, right? Y go from x to 2 minus x squared, and then x gonna go from, that we know is from 0 to okay, intersection. X equal 2 minus x squared, so x squared plus x minus 2 equal to 0. X plus 2, x minus 1. Well, we are interested in x equal 1 here, so it's from 0 to 1. Okay, from here we can set up a double integral to compute the mass, and then just compute this thing here. It shouldn't be too bad. Mass is double integral over the region D of the density times area. Okay, double integral over the region D. Well, 0 to 1. X 2 minus x squared. Rho xy is 3 xy dy dx. Let's work it out real quick. It shouldn't take you that long to do it on the exam though. 0 to 1, and 3 over 2 x y square x 2 minus x square dx. 3 over 2x, and then this we are 2 minus x square minus x square dx. Oh man, I was planning the 3 of 2 outside, so it's going to be a 4 minus 4x squared plus x to the 4th minus x squared dx. What do we have? We have a 4x that minus, so it's going to be minus 5x to the 3 and plus x to the 5 dx. Okay. Man, might as well put the 3 over 2 outside. 4 over 2x squared minus 5 over 4 x to the 4 plus 1 over 6 x to the 6. 0 to 1. Oh, how nice. Let's plug in number 1 in there. 4 over 2 minus 5 4 plus 1 over 6. And ta-da. The common denominator is 12, right? So it's going to be a 3 over 2 times 24 over 12 minus times 3, 15 over 12 plus times 2, 2 over 12. 3 over 2, and what do we have? We have a 24 minus 15, that's 9. 9 plus 2 is 11 over 12. So 33 over 24. Of a thin plate. Okay, we're gonna go from the beginning here, right? So in order to get to a thin plate, it makes sense to go from a thin rock. Okay, on x-axis. So of course, if it's a rock, you put on the x-axis. Put this on the x-axis here. So what happened is that we're gonna have two mass here. So it's gonna be a mass 1, and somewhere it's gonna be a mass 2. Not exactly the same though. The center of mass is gonna be somewhere not in the middle. Let's say that this is the center of mass there. X bar. So for at M1, we can have an X1 right here. At M2, we can have an X2. And then we have the distance from X1 to X bar and X2 to X bar. X bar minus X1, X2 minus X bar. Distances. Well, X bar is the center of mass. M1 X bar minus X1 has to equal to M2 X2 minus X bar. Okay. What do we have here? From here, we can solve for X bar, right? So work it out and solve for X bar. M1 X bar minus M1 X1 equal M2 X2 minus M2 X bar. Right? So move the X bar to the other side and move X bar M1 plus M2 M1 X1 plus M2 X2 so I mean X bar, the center of mass, right? Is the M1 X1 plus M2 X2 over M1 plus M2. If masses are located at X1, Y1, right? X2, Y2, and dot, 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 Xn, Yn, then we're going to have the summation of everything here over the smaller masses. So what we have is that I'm gonna call this to be a m, right? It's the moment of masses, and it is the mass. So that I can shortcut my life here. M over m. It's the moment of mass. And this is just the mass here. Well, for the masses located at the point, we have a moment of mass about the y-axis and about the x-axis. Have a moment of mass about y-axis, and then we also have a moment of mass about x-axis. Okay, so about the y-axis, then you're gonna have to sum them all up. Let's see, it's gonna be m1 x1 m2 x2 all the way up to mn xn. This is the, well, my m1 x1 plus dot 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 plus mn xn. A lot of people would just use the summation here. I go 1 to n mi xi. For the moment of mass about the x-axis, then it's going to be mx, and then it's going to be a m1 y1 plus dot 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 plus mn yn. So use the summation notation mi yi. The moment of mass here, you can think of it as a rotational tendency. Some people say moment of mass, some say moment of the system. In the textbook, they call it moment of the system. So that is the same as the rotational tendency, a thin plate. For a thin plate, the moment of mass is gonna be the double integral because we're going to sum up all over the region D. And then same thing here. For the moment of mass is about the x-axis, that you have a double integral. So I'm going to introduce the center of mass there. Has center of mass x bar. Well, we know x bar is the moment of masses divided by mass, right? So it comes from the thin rod here. So the moment of mass, well, we have moment of mass about the y-axis, and then we also have a moment of mass about the x-axis. For the moment of mass about the y-axis, then it's going to be x bar. And as you can see, you have these x1, x2, xn here. The x is the distance to the y-axis. So we know the mass, right, is double integral over the region D. Rho x, y, dA. And then for the moment of mass, look at this one here. It's the sum of the mass multiplied to xi. So xi is the distance to the y-axis. Well, the distance to the y-axis is gonna be x. So that's why you have a double integral over the region D. X times the density is rho x, y, dA. For a sample mass, let's see, the distance to the y-axis is x. As you can see, this distance here is x. And the distance to the x-axis is y. Okay. X, y. Everybody see this? That's why you have this formula. So similarly, y bar is going to be a moment of mass system, moment of the system about the x-axis over the mass, and you're going to be this thing here. Yeah, this is the reason why I don't put this on the exam. It takes a while to get the center of mass here. Yeah, okay, so this is the center of mass. X bar, Y bar. Okay, so here comes number 3. Moment of inertia. Of a thin plate. Okay, so the moment of inertia comes from rotation, and you got to rotate something in order to get this. Okay, so here comes an object. I said that we have an object right here. And there's a force that is pushing the object to rotate. So here comes the force here. And then the object is gonna, as you can see, this is the rotational tendency, so it's gonna rotate in a circle. Force is gonna push the object to do a rotation. It's ugly circle, but what? For the rotation, we have a center, right? And this is the radius of rotation. Newton, second law of motion. Now, let's take a look at it. Everybody know this. F is equal to force is mass times acceleration. Well, this is an angular acceleration. So the acceleration is going to depend on the radius. M, acceleration here is R alpha. I'm going to have some notation. So the alpha here is the angular acceleration. Okay. What we're gonna do here is that we're gonna do something to this formula. We can multiply both sides by R. Multiply by R. It's the radius R. So if we do that, we're gonna get a RF equal mr square times alpha. Okay, the radius times force. You gotta learn this one from math 1C. This is notation for the torque. So this is the torque, right? And then mr square is very famous too. It's the moment of inertia. Okay, so that's it. That is the nice formula that we get from Newton's second law of motion. What this formula tells us is that this is what it tells us. That I'm gonna type it up nicely here. Oh, it's a nice color here. Moment inertia. determine the torque needed for a desired angular acceleration. If we rotate a thin plate with density rho x, y, we have moment of inertia about the x-axis. That is Ix. According to here, it is the mass multiplied to the radius square. Well, radius is the radius of the rotation, so that is the distance to the x-axis. Gonna be a double integral d, right? It's the radius of the rotation, the distance to the x-axis square. So that's gonna be y square, and then the mass is rho xy dA. It's the m. This is the r square, m r square. Sum them up. Okay, we also have a moment of inertia about y-axis. Ix equal to, not Ix though, but the y-axis. So Iy double integral over the region D. Oh, double integral look ugly. X square rho xy dA. We also have a moment of inertia about the origin or the center of the plate. Yeah, usually the plate is gonna be circular, because if it's circular, then you can do many things with it. If it's not circular, then you cannot do much. It has to be circular. It has to be a circle. Okay, so moment of inertia about the origin is gonna be well, the distance to the origin is x squared plus y squared. Mass rho xy dA. Well, for the moment of inertia about the x-axis and the y-axis, you can see them as the swinging motion. And then moment of inertia about the origin. Well, you don't swing it. This one, you're gonna do rolling. So it's rolling motion. Yeah. I got to cover this thing in case you take the probability. So that is the probability. For those of you who want to be an actuary. An actuary. From calculus 2, we know that the integral from a to b fx dx is the probability of a continuous random variable having density function fx Okay, for a density function fx there, just a little review for you. In order for fx to be the density function, right? So the integral negative infinity to infinity fx dx must be exactly 1. In this section, for a pair of continuous random variable, okay, such as height and weight, like have two components. Of a machine. Two different waiting time and many more. Well, we have a John density function. Fxy, and its probability within the region D is this one. Double integral over the region D, fxy dA without proper manner. The time failure in man up to aircraft sensor can be expressed as this one. Rho xy, you know why rho? Because this rho is density. You can change this one to rho or f up to u. But just let's just use rho for density here. 1 over a64 e to the negative x over 24 minus y over 36. For x more than 0, y more than 0, and it's going to be 0 otherwise. Yeah. Set up the integral to find the probability that neither sensor function after 2 years. 2 years. 24 months. Right? And then we know that the time is x and y. The sensor 1 has the time x, sensor 2 has time y. So how would we set this thing up? Well, there's the probability that neither of them sensor, so both of them gonna fail. Huh? 0 less than equal x less than equal 24, and 0 less than equal y less than equal 24. Huh? Okay. Well, 0 to 24, oh, they're the same, so it doesn't matter which one go up first though. 1 over 184 e minus x over 24 minus y over 36. And you can do dx dy or dy dx there. It's the same. Right. So there's the setup here. You just got to evaluate this double integral to figure out the probability. You can try this thing for fun, right? Try it. And you will see that the answer is going to be 30.8%.